Recording is rolling. It is Wednesday, November 2nd. Today's going to be a lab day. So we've got the launchers back. Actually, let me borrow this one and just like use it for a for demo for you guys. Brings back to you though. All right. So we got the launchers back from the projectile lab days. We're gonna kind of repeat that lab except throw on one more step. And the question we're trying to figure out is what is the spring constant of the launcher? Because you guys know there's like a spring here. You're gonna take a ball. You guys remember the technical process of this. We're gonna take the ramrod, smash this first. Now, if you remember back from a few minutes ago, you guys remember there's like it can go 3 clicks, click, 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 3 clicks, right? So how many clicks you do, just keep that consistent over the course of your lab with your teammates, right? So if you do 3, then just always do 3. If you do 1, just always do 1. Right? You guys get the idea, right? And then one thing you're have to measure is, well, like how far did you smash it? How far did you compress it? Because we're playing well far into the semester where, I mean, that's gonna be one thing you have to measure, right? How far did you compress that? Right? Maybe some number of centimeters. Let's see. Actually, we try and get the answer here. It's probably like this right here, probably, or like however far that is. Okay. Let me do an example with you guys. So suppose, just for instance, you come up with like 5 centimeters. Maybe that's what you come up with. When you do your calculations, are you going to go x equals 5 of anything? 5 centimeters? Guys, how many meters is equal to 5 centimeters? 0.05. Okay. All right. So just think ahead a little bit here. Okay. I'm going to have you guys do a full AP style write up with this. I gave you guys some paper on your desk, right, and some colored pencils. So in a few minutes, we're going to head out. You guys remember the 5 parts of this. So the question you're chasing down is, what is the spring constant? We're going to use this particular method, like exactly what I said here. You're going to go to the top of the balcony, blast these balls out horizontally, see where it lands, right, and then do some calculation. Okay? You guys have to list your measuring tools. I will give you guys a hint for one of these, or save everybody's step. Those balls that you guys have are, I measured them this morning. I got like 6.4 grams for a few of them. Okay. Again, in your calculations, you're going to run the numbers in kilograms, right? You guys know that, right? So don't do 6.4 for any mass numbers. You're going to do 0.0064 to represent the number of kilograms, right? Mass is equal to that many kilograms. Okay. Right. So procedure is just here. I measured this quantity using the meter stick. I measured this quantity using a scale. I measured this using a ruler, right? So whatever you're measuring is what you're gathering, right? Use tools to measure this thing. Okay. Analysis, apply equations. I'm giving you guys way too many hits here, but I'm trying to save everybody time. Right, and then the conclusion is going to answer your question. The question, of course, is what is the spring constant launcher? We're doing this particular method. Okay. Right. So you guys kind of wrap your mind around what we got so far. Okay. So I'm going to come back to this page. Let me mention these other things before I get too far in the lab here. Right, so picture retakes are this Friday in the gym lobby. So if you aren't happy with the original picture, then first go to school on Friday. And then I have printed out your guys' next quizzes. So I'm thinking by the end of class today, right? So yeah, end of class today, I do want to pass this out to you guys, to give you guys a few days to work on this. Right, so that'll be done Monday. Okay, guys good? Okay. Now, a few more things to say on this, but we're going to come back and link back to this. Hey, look, it's the same setup, isn't it? Right, launcher and horizontal, top of the ledge. Okay. Now, yesterday when we were going through AP Classroom, there were 3 problems we didn't get through to, and one of them was exactly the setup. Okay. Also, this is set up for today's lab, and also there's a quiz question that I asked you guys. That's right. So we got like 3 reasons that this is going to be relevant. Okay. So suppose right now you guys could just use the same mass over and over. Okay. But AP asked a question had to do with like changing the mass of this ball and where it would land. And I asked you guys a very similar quiz question, right, that you guys are about to see later today if you read the quiz today. Okay. So suppose you got a ball with some mass m, and you launch this thing. It goes, lands like right there, right, so some distance d, right, so like some distance d away. Right? And then you go back and you rerun the simulation, except with half the mass, right? Now, whether this is the balls being pushed against a spring, or maybe this is a cannon with a chemical explosion, like right, like blast out of the ball. Right? There's some energy that's associated with that blast, right? Right? Like if the energy came from the spring, it's 1/2 k squared, which has nothing to do with the mass of the ball. Right? But the mass of the ball, like the more massive, what do you think happens to the speed? It's less and less, right? Right. So the amount of energy in the system is independent of mass, but the speed is probably inversely proportional, right? Like the more massive the ball, the slower it's going to go, right? So if you make the ball less massive, it's going to fire out further, right? Uh, let's pop in a specific ratio of masses and see if we can walk through like where it would land. Okay. Um, so I set up energy conservation because that's our thought process, our framework for solving these. Okay. And there's some quantity of energy, whether it's a spring-loaded cannon or a chemical cannon. Okay, let's go with the springs, and I'll call it 1/2 kx squared. Okay, but it really doesn't matter where the energy is coming from because it's just some quantity of energy. You could call it like 100 joules or something like that, right? Let's say you have like 100 joules of energy in the system. Okay, now if I'm doing conservation of energy from here to here, right, point A to point B, initial, final, right? You guys get that? Right. And that's my entire system. I'm ignoring the fact that there's like some height change. I don't care about that. All I care about is I'm just like hard focused on this. Okay. Then what's the only type of energy right here? It's just kinetic, right? Okay. Right. So when this all turned to 1/2 mv squared, okay. See, like I could solve this and I could see what is the blast speed. Right? The V is like the blast speed. You guys see that? Okay. All right. So there's some quantity of energy, right? Regardless of where it comes from, it's like 100 joules, for example, right? And it's equal to this expression. Okay. So what if you had the exact same amount of starting energy? Okay, it comes from a spring cannon. Okay, and you use a ball that has half of the mass, half of the mass. Right. So is the speed going to be greater or smaller than the original V?
Greater.
Yeah, it has to be greater, right? It's going to be blasted out faster, right? Okay, so it's going to land further away, right? Right now, it could do this more formal way and write out like a giant proof and take ratios and blah 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 and get to the answer, right? But we've done plenty of those by this point in the class, so I want you guys to see us like forest for the trees, big picture, just all in one step, all in one like tidy expression right here. Right? Did anybody figure out, or can you figure out right now, what factor V has to change by? You guys just told me it's going to be greater than 1. Right? It's going to be what times V? Is what? Square root 2, right? Leonardo says square root 2, right? You guys agree with that? Square root 2, right? Square root 2, which is about 1.41, right? Because watch this, guys. What's the square root of 2 squared? 2. What's 2 times this half? 1, which just goes back to the original expression, which conserves the original amount of energy, right? Yeah. So square root 2. Hey, if this is blasted the square root 2 faster, right? Does the time of fall change? No, the height doesn't change, the time of fall doesn't change. So what is the blast distance going to do? It's going to increase by what factor? Also the square root of 2, right? Because this distance, the square root of 2 times the original distance, right? Okay. So the distance in general, maybe, like some here, I'll call it D, but you guys, yeah, is this horizontal speed, which is the blast speed, is the horizontal component of blast speed, times the time of fall. Right? Now the time of fall doesn't change, height doesn't change. If you just drop the ball, also the same. These would all tie. Right? Time fall is the same. Okay? If you throw a factor of square root of 2 on the V, you see there's also going to be a factor of square root of 2 on the V. Is there also a factor of square root of 2 on the D? Right? You guys see it? It's about 1.4 times as far. Okay, you guys see it? Okay. All right, so that'll help you with the one we didn't get to yesterday, also help you with the quiz question, and also it helps you sort of think about what we're doing with this lab today, because it's a very similar process we're going through. Okay, so here's I'm giving you guys way too much of the answer, but this is what you have to figure out by yourselves. Okay, you have to say, okay, if I know this height of fall, I can calculate the time of fall. So don't include a stopwatch today. I mean, I guess you could, but it's not a very accurate way to do it. I'm gonna have you guys calculate the time of fall based on this height of fall. Is that okay? Right. And if you know the time of fall and how far it goes distance, can you very quickly get the blast speed? Right, that's just what I wrote right here. That's that, right? So you can calculate the blast speed. If you can calculate the blast speed, can you go up and set up a conservation of energy like I was just sort of showing right here? Right? And then calculate the spring constant. You guys see that? Right? And can you guys do the 5-part write-up on that blank paper I gave you? And then you can grade with the color pencil after we come back from outside. Okay, great. You guys see all that? Okay, who's got any question? Any question? All right, so rest of class, we're gonna go outside on the balcony, blast off 2 or 3 launches, make some quick measurements, then we'll come back in class. Give you guys a few minutes to finish the write-up, then we'll grade the write with the color pencils. And I want to get you guys your take-home quiz before you walk out of class, so you have a few days to do it. Because I know you still haven't quite got to the text of problems. I have tomorrow to do that. But I know it's yeah, I know it's a lot of stuff, but I mean, physics just takes a lot of time to work with. Right, so you guys ready to head outside? Outside? All right, so I'm going to stop this recording. All right, we're about to head outside and do this lab, gather some empirical data, crunch some equations, do a lab write-up.